Welcome! In this video, we'll be tackling a classic trigonometry problem. Our objective is to solve the equation cosine of x plus cosine of 2x equals 1. By the end of this lesson, you will be able to solve trigonometric equations that involve both single and double angle expressions. You'll learn a step-by-step method to simplify these equations and find all possible solutions. So, our main goal is to find all the angles, x, that satisfy this specific equation, cosine of x plus cosine of 2x equals 1. Let's look at the equation again. We have cosine of x and cosine of 2x. The fact that one term involves a single angle, x, and the other involves a double angle, 2x, is a problem. We can't easily combine these terms. Our first strategy should always be to simplify the equation, and that usually means getting all the angles to be the same. This way, we can treat the equation as a polynomial. The tool we need here is a double angle identity. Remember, these are formulas that relate a trigonometric function of a double angle to functions of the single angle. The double angle identity for cosine has 3 different forms. Let's write them down. Take a moment to look at these. Which one do you think will be most helpful for our equation? Remember, our equation already has a cosine of x. The best choice is the second identity. Cosine of 2a equals 2 cosine squared of a minus 1. Why is this the best choice? Because it allows us to replace cosine of 2x entirely with an expression that only contains cosine of x. This gets rid of the double angle and lets us proceed. Okay, let's now apply this identity to our equation. Our original equation is cosine of x plus cosine of 2x equals 1. Using our identity, we'll replace the cosine of 2x part. So, the equation becomes cosine of x plus, in parentheses, 2 cosine squared of x minus 1, all equals 1. Excellent. Now we have an equation that only involves the single angle x. We've simplified it. Let's clean this up. We can remove the parentheses to get cosine of x plus 2 cosine squared of x minus 1 equals 1. Notice what we have. It looks very much like a quadratic equation. It has a term with cosine squared, a term with cosine to the first power, and a constant term. Because this is a quadratic-like equation, our next step is to set it equal to 0, just like we would with a standard quadratic. So, we start with our simplified equation, 2 cosine squared of x plus cosine of x minus 1 equals 1. Let's subtract 1 from both sides of the equation. This gives us 2 cosine squared of x plus cosine of x minus 2 equals 0. Now, to make this even clearer, we can use a technique called substitution. It's a great way to handle more complex-looking equations. Let's define a new variable, u, and set it equal to cosine of x. This is just a temporary substitution to help us solve the equation. Substituting u into our equation, we get 2u squared plus u minus 2 equals 0. Now it's a perfectly ordinary quadratic equation that we can solve. So we need to solve the quadratic equation 2u squared plus u minus 2 equals 0. Let's see if we can factor it. We need to find two numbers that multiply to 2 times minus 2, which is minus 4, and add up to the coefficient of our u term, which is 1. Are there any two integers that do this? The factors of minus 4 are 1, minus 4, minus 1, 4, 2, minus 2, and minus 2. 2, none of these pairs add up to 1. This tells us that the quadratic equation does not factor nicely using integers. That's okay. We have another reliable tool for this situation, the quadratic formula. Here is the quadratic formula. Take a moment to recall it. Let's identify the coefficients in our equation. A is 2, B is 1, and C is minus 2. Now we substitute these values into the formula. This gives us u equals negative 1 plus or minus the square root of 1 squared minus 4 times 2 times negative 2, all divided by 2 times 2. Let's simplify this step by step to avoid errors. First, the term under the square root. 1 squared is 1. The product, minus 4 times 2 times minus 2, is 16. So we have the square root of 1 plus 16, which is the square root of 17. Our denominators are both 4. Putting it all together, our solutions for u are negative 1 plus or minus the square root of 17, all over 4. These are the two exact solutions for our quadratic equation. So we have two potential solutions for u, but remember, our variable u is just a placeholder. It represents cosine of x. So, we have two possibilities. Either cosine of x is equal to -1 plus the square root of 17 over 4, or cosine of x is equal to -1 minus the square root of 17 over 4. Let's analyze these two cases. Let's start with the second case, case 2. The square root of 17 is approximately 4.12. So we have -1 minus 4.12, which is -5.12, divided by 4. This gives us a value of approximately -1.28. Can you see a problem here? A cosine function can never be less than -1. Since -1.28 is outside the valid range of -1 to 1 for the cosine function, we can confidently discard this solution. It yields no valid angles. Now let's examine the first case. Case 1. We have -1 plus the square root of 17 divided by 4. This is approximately -1 plus 4.12, which is 3.12, divided by 4. This gives us approximately 0.78. This value is definitely within the range of -1 to 1. This means case 1 is a valid solution that will give us real angles. Let's move on to find those angles. Our task is now to find the angles x for which cosine of x equals this specific value. Let's call this value k. So we are solving cosine of x equals k, where k is our value from the quadratic formula. To do this, we use the inverse cosine function, sometimes written as arccos. This function gives us the angle, whose cosine is k. The principal solution, often denoted x1, is given by the arccosine of k. Using a calculator, this value is approximately 0.675 radians, or about 38.7 degrees. But is this the only solution? No. The arccosine function only gives us an angle in the first or second quadrant. Because cosine is positive, our principal angle is in the first quadrant. However, the cosine function has a period of 2 pi, and it's also positive in the fourth quadrant. So we need a second solution in the fourth quadrant. We can find this by subtracting our principal solution from 2 pi, or 360 degrees. The second solution, x2, is 2 pi minus our principal solution. This is approximately 5.608 radians, or about 321.3 degrees. And finally, because the cosine function is periodic, all solutions will be these two solutions plus any integer multiple of 2 pi. So we write our general solutions as x equals 0.675 plus 2 pi n, and x equals 5.608 plus 2 pi n, where n is any integer. These formulas capture all the infinite solutions to our original equation. There's one other possibility we need to check, and it's a bit more subtle. Look back at the very first step of our simplification. We started by simplifying the double angle cosine of 2x. Is there any other way to simplify cos 2x that we missed? Let's go back to our three identities. We used the one in the middle, 2 cos squared x minus 1. But what if we use the one on the left, cos squared x minus sine squared x? Let's substitute that into the equation. It's a great example of being thorough. This gives us cosine of x plus cosine squared of x minus sine squared of x equals 1. This seems worse, right? Now we have both cosines and sines, but we have a powerful tool that can relate them. Remember the fundamental Pythagorean identity. It tells us that sine squared of x plus cosine squared of x equals 1. We can rearrange this to say sine squared of x equals 1 minus cosine squared of x. Let's substitute this back into our equation. Take a moment to think about what will happen. Our equation becomes cosine of x plus cosine squared of x minus, in parentheses, 1 minus cosine squared of x equals 1. Let's distribute that negative sign. We get cosine of x plus cosine squared of x minus 1 plus cosine squared of x equals 1. Notice the sign of the second cosine squared term. Combining like terms gives us 2 cosine squared of x plus cosine of x minus 1 equals 1. This is the exact same equation we solved before. So, using a different identity, let us write back to the same quadratic. What about the third identity, cos 2x equals 1 minus 2 sine squared x? If you substitute that into the equation, you will quickly find that the one terms cancel out, and you are left with an equation involving only sine and cosine. If you replace sine squared with 1 minus cos squared x, you'll end up with 2 cos squared x plus cos x minus 1 equals 0. Once again, it leads to the same quadratic, so all paths lead to the same solution. So, we've solved the problem. Let's quickly recap the steps we took. First, we identified that the equation had mixed angles x and 2x. Second, we used a double angle identity to rewrite the equation so that it only contained the single angle x. Third, we rearranged the resulting expression into a standard quadratic form, which we could make simpler using a substitution. Fourth, since it didn't factor, we used the quadratic formula to find the two solutions for u, which represents cosine of x. Fifth, we analyzed these two solutions and rejected one of them because it was outside the valid range of the cosine function. Sixth, we used the inverse cosine function and our knowledge of the unit circle to find the two principal angles in the first and fourth quadrants. And finally, we added 2 pi n to our principal angles to get the general solution that includes every single possible answer. You now have a complete method for solving these types of trigonometric equations. Thank you for watching. Okay, that covers the core method, but what if you wanted to check your answer? Let's quickly verify one of our solutions. We found that the first solution is x equals arc cos of -1 plus the square root of 17 divided by 4. This means that cosine of x is equal to k, where k is our quadratic formula result. Now, let's plug this back into the original equation, cosine of x plus cosine of 2x equals 1. We'll substitute k for cosine of x. We know that cosine of 2x is 2 cosine squared of x minus 1, so that becomes 2k squared minus 1. This simplifies to 2k squared plus k minus 1 equals 1, or 2k squared plus k minus 2 equals 0. But what is this? This is exactly the quadratic equation that we solved earlier. By definition, the value k that we found is one of the roots of this quadratic. Therefore, when you plug it into this equation, the result must be 0. So, we're left with 0 equals 0, which is a true statement. This confirms that our solution for x is correct. It's a powerful and satisfying way to check your work. And that truly concludes our session on solving trigonometric equations involving double angles. Great job!